if you please tell me if you can't see it. Okay, so the subject today is a little bit on the outskirts of numerical linear algebra, but perhaps has some relations to Elizabeth's talk, and that is taking advantage of the easy differentiability of neural networks to construct Jacobians, essentially. And the application for this I'm going to present today is in numerical weather prediction. So I'm going to dive right in and explain the context for this research, which is an algorithm known as data assimilation, or rather a class of algorithms known as data assimilation. And for those who are not familiar with this class of algorithms, it is essentially for synchronizing a model with the real world via observations. So one example is what we call 4D VAR, which is the four-dimensional variational algorithm. This is the one that we actually use at the European Weather Centre. And the purpose of this algorithm is to construct a trajectory of our numerical model that minimizes the distance to certain observations across a window of time, say 12 hours. So these observations, they just come from, weather balloons, buoys, satellites, etc. But they don't cover the Earth comprehensively in space or time. And so in order to construct a trajectory, we have to blend these observations with a numerical model, essentially to fill in the gaps, the areas that we don't observe. So what we do is we define an objective function or cost function, which measures the least squared distance between a trajectory of our numerical model and these observations. And then we use some kind of gradient descent algorithm or Krylov subspace method to minimize this cost function, giving us a more accurate model trajectory. In this case, it's the red line. So in order to do this procedure, we require three forward operators, and I'm using the word forward operator here very loosely. So the first one is the obvious one, the nonlinear model. This is an atmospheric model that advances an atmospheric state from one time to the next. So we feed in an initial state, x0. This is simply a list, a concatenated list of all of the variables of the atmosphere, that's pressure, temperature, wind speed at every grid point over the globe. And it gives us the evolved state of the atmosphere over that time. So we require not just this non-linear model, but also what we call the tangent linear model, which is just jargon. It's nothing more than the Jacobian of the non-linear model evaluated about this non-linear trajectory. So the tangent linear model allows us to evolve in time a perturbation to an atmospheric model state. And I represented this here by delta x0 instead of x0. Now, of course, the equations that describe atmospheric flow are non-linear, and so perturbations are not evolved in the same way that full model states are. So we require the Jacobian in order to do this. And if you imagine this linear model as a matrix applied to delta x0, then we can construct something else called the adjoint model, which is nothing more than its transpose. Of course, we only deal with real numbers in atmospheric modeling, and so the transpose and the adjoint are the same in this case. We just call it the adjoint for full generality. The adjoint model is quite a difficult thing to get your head around, but the best way to think of it is it allows you to propagate gradients of scalar functions backwards in time. So let's suppose our cost function is evaluated at a later time. This is j. It's just a scalar cost function that's a function of the variable. The adjoint model allows us to propagate that backwards to the beginning of the initial of the assimilation window. Now, to give you a bit more examples of these, how they're written mathematically, the nonlinear model is very simple. It's just an nonlinear operator m. We feed in x0 and it gives us xn, which is a time-evolved atmospheric model state. Tangent linear model looks similar. In this case, it's an upright linear operator evaluated about the nonlinear trajectory, which we, in this case, apply to a perturbation. And the adjoint model, as I said, is the transpose of this linear operator, and we use that for propagating gradient. And I've shown here some pseudocode, which looks like Python. You don't need to concentrate on this too hard. It's just if you're curious how these different models are actually implemented in practice. So these three models have to be consistent with each other. They have to satisfy certain criteria in order for data assimilation to actually work correctly. One of those I've shown here. This is actually the definition of the adjoint model with respect to the tangent linear model, where delta x and delta y are just arbitrary small perturbation vectors. So once we've constructed these models, once we've written the code, we have to check whether they satisfy these criteria before we really use them to do any data assimilation. Now, I'd like to talk a bit more about how atmospheric models themselves are constructed. So this is kind of a crash course in numerical weather prediction. We like to say that atmospheric models can be decomposed into two components. They're what we call the dynamics and what we call the physics. So the dynamics, you can think of that as the resolved fluid flow of the atmosphere. So we essentially use a cut down version of the Navier-Stokes equation to model the weather. And so we have to discretize the entire atmosphere into grid boxes across the whole globe. And anything smaller than the grid box size will not be resolved. So the resolved flow we call the dynamics, and the unresolved flow we call the physics, which is quite a stupid label, to be honest, but that's what we call it. The full name being physical parametrisations of unresolved processes. I've given a couple of examples here. For example, convective clouds or cumulus clouds, the ones you might see on a sunny June day over a field. These are, by our perspective, very large, but according to the atmospheric model, they're actually quite small. The highest resolution model we use at the European Weather Centre is only 9 kilometers resolution. And so these clouds are actually too small to be represented. So instead, we parameterize their effect on the resolved flow in a statistical way, and we call this a parametrization. Another example I've shown here is gravity wave drag. This is the one I'm actually going to focus on today, and I'll explain that later on. So in order to construct the tangent, linear, and adjoint models of a full atmospheric model, we have to do it for the dynamics and the physics. Generally speaking, writing tangent, linear, adjoint code for dynamics is actually quite easy, but for physics, it's generally very difficult because those physics subroutines, they tend to be very esoteric. They're written by a domain specialist, someone who is really good at understanding clouds and not much else. So the code itself is often quite difficult to process. But also physical parameterizations often involve sharp nonlinear processes. For example, you click your fingers and a cloud appears. There are many if statements and step functions which are difficult to linearize. And so constructing the tangent, linear, and adjoint models of physics subroutines is hard. And so we want to find any way that we can to help this process. So what I'm going to propose today is quite a simple idea. What we're going to do is train a neural network to emulate, to act as a surrogate for an existing physical parameterization subroutine. So it's going to be a drop-in replacement for just a Fortran subroutine that hooks up with the rest of the code nicely. Then, instead of coding the tangent, linear, and adjoint models of the original physics scheme, which, as I said, is quite difficult, we're going to do that for the neural network, which is trivial. And that's because neural networks are, by design, easily differentiable. And they have to be in order to train them through backpropagation. Then I propose to do data assimilation with these tangent, linear, adjoint models based on the neural networks instead of based on the original linearized physics code. So I can think of a couple of advantages to this. Really, I'm doing it out of curiosity, but the code will be much more compact than the original code. Tangent, linear, adjoint code is notoriously messy and difficult to read. But the neural network code that I've already written is quite compact, and we only have to write it once. So in principle, we can reuse this neural network code for many different physical parameterizations, not just the one that I'm focusing on today. And secondly, the neural network evaluation itself is really nothing more than a bunch of matrix-matrix multiplications evaluated at every grid point. And this is exactly the kind of operation that you could outsource to an accelerator like a GPU. So in principle, it could actually accelerate the code. So the physics scheme I've chosen is something called nonorographic gravity wave drag. This is gravity waves. That's nothing to do with these relativistic gravity waves. It's simply a coincidence of terminology. And what the scheme describes is how waves, density waves, which are triggered in the troposphere at the bottom of the atmosphere, propagate up to the top of the atmosphere where they break, just like how the waves on a shore might break, where they deposit momentum, essentially acting as a drag force on the wind there. And so the input to this physical parameterization routine is a column of atmospheric variables. So there's no consideration of the horizontal, it's all vertical. And the output is a a column of wind tendencies at that same co-located point. So we're basically modeling the drag due to these breaking waves. And I'm going to be testing this idea inside our state-of-the-art atmospheric model, which we call the Integrated Forecasting System, or IFS. And the chosen neural network architecture is deliberately simple and bog standard, as they say. It will simply be a fully connected multi-layer perceptron with hyperbolic tangent activation functions. So this is really nothing state-of-the-art, none of this ReLU activation or convolutional layers or anything like that. I wanted to keep the code as simple as possible so that I can differentiate it easily. And I won't talk about the training methods. Suffice to say that we successfully trained a good surrogate for the existing subroutine. Okay, so before we test this idea in the full atmospheric model, I want to show to you that it does pass the tangent linear adjoint tests that I mentioned earlier. The first one, which I've already mentioned, is to check whether these two expressions are the same. Now, because in reality, this M applied to delta X is actually a Fortran subroutine, it's using floating point arithmetic. And so we shouldn't expect these two to be exactly the same, but rather to be similar to at least the machine epsilon. So the left-hand side and the right-hand side, the normalized difference should be around 0 with 16 decimal places, followed by 1. And suffice it to say that the test does pass in this case. I've tested this on my hand-coded neural network linear code, and it works. The second test is to test whether the tangent linear model is a good linearization of the nonlinear model. So we're essentially checking the size of the second term, or the first term, if you count it from 0, of a Taylor expansion. So we want this epsilon to be as small as possible. Now, in reality, it won't actually be completely 0, even if M is perfectly coded, because the atmosphere does not, it's not a linear system. Errors grow non-linearly. But we at least want epsilon to match the epsilon from the existing state-of-the-art code. So that's what I'm showing here for 3 variables: temperature, zonal wind, and meridional wind. That's eastward wind and northward wind. I'm showing as a function on the y-axis of the model level. So this is the bottom of the atmosphere and this is the top. I'm showing you the relative change in epsilon when we use neural networks instead of the state-of-the-art code. And in this case, this is the relative error. So you can see that epsilon is actually below 0 for most of the atmosphere, which means that when we use neural networks, our tangent linear models are actually better approximations to the nonlinear model than they were before, which is, I think, quite surprising. And so I've actually put this back into our real atmospheric model and used it to perform weather forecast tests with data assimilation. And the take home from this figure is that the neural network gives essentially no change in the forecast scores. So what we're seeing on the right here is an error, a temperature error difference between 2 experiments. So we want this to be 0, or at least 0 or negative. We don't want it to be positive. And we're showing it for a few different lead times going into the future. So starting with 12 hours, going up to 5 days, that's T plus 120. So you can see a lot of blotches here. It's not exactly white, but suffice it to say, our algorithm does add hatching when there is statistical significance. And in this case, there's basically none. So this noise here is not statistically significant. In other words, when we use a neural network, we see no change in the forecasting error. So in principle, if we were to put this back into our operational system, we could use it to do actual weather forecasting and we wouldn't see any degradation. Now, a few further experiments I'd like to try. I mentioned that there could be computational savings because of the simplicity of the neural network evaluation, but actually the neural network code is about the same speed as the existing one, if not slower. It's very hard to beat systems that have been optimized in an operational setting for 10 or 20 years. So as I said, maybe it's worth trying it on a GPU. So you could imagine outsourcing the evaluation of this neural network to a GPU, and that should be much faster. Secondly, there might be a possibility here to actually improve the weather forecast skill by training the neural network on a more physically realistic parameterization instead of the one that I did here. And the neural network is the same cost regardless of how accurate it is a surrogate for reality. So if we could find a way to improve the realism of the neural network by training it on a more complex but expensive scheme, we might actually be able to improve the forecast scores. So that's basically, I'm going to finish there and say that neural networks can be differentiated trivially by design. And so they're the ideal building blocks for these Jacobians, tangent linear and adjoint models, which are essential to doing 4D via data assimilation. I've done some preliminary tests with a specific physical parameterization scheme, and I found that, well, I would say they were successful because there was no degradation in the skill of the weather forecasts. But it's very difficult to match the computational performance of the existing Fortran, and so getting there will require some more effort. So thank you for listening.
Thank you, Samuel, for your wonderful speech. Catherine, is there any questions on Zoom?
There aren't, but I will again ask a question just so that the speakers have questions. I was curious if, I guess you touch on this a bit by measuring degradation, but since you're replacing physical properties by very simple neural networks, essentially, are you concerned that you're not approximating the correct thing physically? Or does that not seem to show up?
Well, we've compared the subroutine that we're trying to emulate with our emulation offline. So we've just compared the numbers to see if they give the same outputs from the same inputs. And that is pretty much the case. So we're confident that our surrogate is a pretty good surrogate for the existing subroutine. Yeah.
When you say compare the numbers, are they up to what order of accuracy? Are they the same?
Oh, I don't know the numbers off the top of my head.
Okay. Okay.
But we've tried quite a few different architectures and training schemes. Okay. We've tried many different things. It's not a perfect surrogate, but that doesn't seem to be resulting in degraded weather forecast skill in this case.
Cool. Okay. Jemima, is there any questions on YouTube?
No, but I have some questions. So one of the annoying things about adjoint code is that if you make a change to your model, you have to go and change your adjoint, which can be really difficult, right? So what, in terms of the neural network, you could just rerun it if you had like a big code change to your model, but could you actually, do you think there's a way to reuse the existing neural net to make that process?
Yeah, so in this case, the nonlinear, the tangent linear, and the adjoint all share the same hyperparameters. And so if there's a modification to the nonlinear code, all you have to do, and well, of course, this is not quite as trivial as I'm presenting it, but all you have to do is retrain the nonlinear neural network, and you can then reuse those same hyperparameters in the tangent linear and the adjoint model automatically. The actual code doesn't have to change. So in principle, this technique could save a lot of manual labor.
Yeah, for sure.
You know, at the European Centre, we actually have 2 full-time staff just for managing the tangent linear and adjoint models. So they're quite nasty things to deal with.
Great, thanks.
Okay. No thank you for our two speakers. Great talk.
Thanks.